Now we're going to talk about word-to-vector embeddings. Word-to-vector embeddings are very interesting for unsupervised learning because they represent an example of a self-supervised loss that is not the same as the one in an autoencoder. So you could get an idea of how to structure other self-supervised losses. Let's see an example of where this arises. So let's take the language processing task sentiment analysis. This refers to when you take in a sentence and you try to decide if the sentence is conveying a positive emotion or negative emotion, or it could be one of a variety of emotions. You see the sentence here called best movie ever, and you want to say positive as an output. So this is one of those many to one sequential tasks. But in the last lecture, we made it seem as if the LSTM would take each of these elements in, remember the sentence, and give you the output. But the LSTM can't quite work like this because each instantiation of the LSTM has the same number of inputs. So best and movie in particular have different number of letters in them. So you can't just directly encode the letters. Instead, what you have to do first for words is you have to have something hierarchical. So you have to have another neural network that embeds the word into a fixed length vector, which you can then feed to LSTMs as an input. And this is where the motivation came in to encode words into fixed length vectors. So this is the famous word-to-vector embedding, which was proposed in 2013. Here, initially, you have a one-hot encoding of the word in terms of the number of words in the dictionary. So suppose you have 10,000 words in a dictionary. Then any particular word would have a 1 in some particular position and 0 everywhere else. This is a very large size input. Now, the neural network that performs this word vector embedding has a hidden layer with a lot fewer neurons, say 300. And this is what comes up with a fixed length embedding. And the task from this embedding layer is not the same as an autoencoder. It doesn't have to recreate this input vector. Instead, it does something else. On other sampled words, which are other elements of this dictionary, it says what is the probability that this word, the input word, co-occurs or occurs in a nearby position as this other word. And so, for example, if you have the word ants, and then you might be saying sentences like the ants are crawling one by one. So crawling is a word that would occur nearby the word ant. And so if you think about other words that would have crawling next to them, it might be bugs are crawling, worms are crawling. And so ants, bugs, and worms would be encoded nearby because they all have crawling and creeping and these kinds of words next to them. But you would not have crawling embedded near ants because crawling doesn't have the same words that co-occur with it as ants do. So it really breaks down words by their semantic meaning in a sentence, meaning what other words would fit into the same part of a sentence. Another example is, I like eating bananas. So what else could go in the position of bananas? It could be apples, oranges. It cannot be horses usually. So it really breaks words by kind of their semantic functioning in a sentence and their meaning. So at the end of the day, the hidden layer does give you the 300 fixed length vector, and this becomes the word vector that you can use as a lookup to feed into your LSTM. But let's think for a minute about the loss function because that's very interesting. This was one of the first examples of a contrastive loss. The contrastive loss for one word, you sample another word and you want it to put together these and give you some probability that these words are nearby. And this is done by a softmax layer where the probabilities all sum up to 1. And the very other interesting thing about this is that this improves if you train it on both positive and negative examples. So you don't have to predict for every word in your dictionary if the word ants is going to occur nearby. You sample some words that could be positive examples and have it say that these are the words that co-occur based on your corpus of documents. And you would have some negative examples that would say, these words never co-occur. And so it turns out that the negative samples improve this. And that's the same for the more general contrastive losses that are arising these days. But they're just actually kind of simpler than the word vector embeddings. So, for example, you could have two handwritten digits and you would decide, should they have similar locations in the embedding or dissimilar locations in the embedding? This has the effect that it pushes similar things together and dissimilar things apart. And so it's a very powerful unsupervised loss function. The interesting thing about the word vector embedding is in some instances, the latent space has a lot of geometric structure. So people have observed that analogies can be worked out using these embedded spaces. So if you're looking at Italy, the general direction and angle at which Bologna, which is a city in Italy, occurs in relation to Italy is similar to the direction where a city in Germany, Hamburg, occurs in relation to the embedding of Germany. And here we see the same thing happening with foods from particular countries, for example, poutine, which is from Canada, and so forth. This doesn't always work perfectly, but it is an indication that a lot of times these latent spaces have a lot of geometric structure such that you could perform vector operations to go from, for example, countries to dishes.